Plastic injection molding is a process which uses a shaping mold to produce a wide range of plastic parts. The process begins when plastic granules are melted and injected into a shaping mold, cooled, solidified, and thereafter ejected. This process is capable of producing parts of varying complexity in a short time frame. The injection molding machine consists of three main parts. These parts include the injection unit, the mold, and the clamping unit. In order to prevent machine downtime and failure, the clamping unit must be maintained properly lubricated. In an industrial setting, the toggle must undergo a large amount of clamping and unclamping cycles. This excessive use eventually causes the lubricating condition of the toggle to deteriorate. Improper lubrication can lead to catastrophic failure. To avoid lubricant failure, machine operators have traditionally relied on their experience paired with a pre-calculated empirical and analytical lubricant life estimation as a guide for determining the relubrication point. This approach, however, lacks robustness and often leads to over-lubrication and lubricant waste. This study, hence, aims to develop a method of real-time condition monitoring of the toggle clamping system using vibration analysis. Thanks to Chenlifa, all testing necessary for this research project were done on the CLF 60TX. At the start of the experiment, the injection molding machine's oil tank was filled with new beta anti-stick industrial oil. After filling the oil tank, acceleration and strain sensors were mounted onto the toggle clamping system and connected to a data acquisition system. During testing, the toggle was allowed to perform a series of clamping and unclamping cycles prior to being relubricated and thereafter repeated. The changes in the system's acceleration profile were recorded and later analyzed using vibrational analysis techniques. The figure on the screen shows the general profile of the data acquired for two cycles. The blue profile represents the acceleration, while the orange profile represents the strain. Via the strain profile, it is possible to clearly see what the toggle is doing. From points A to B, the toggle starts to close. From points B to C, the toggle clamps the shaping mold. Point C to D is where the injection and cooling of the plastic part occurs. From points D to E, the shaping mold is unclamped, and E to F, the toggle reopens. This cycle is then repeated over and over. This study analyzes the vibrational signal acquired during both the clamping and unclamping of the mold. From a tribological point of view, these two periods are the most susceptible to wear and failure, as they exhibit low sliding speeds and high clamping forces. The data collected during the clamping period was analyzed with 4 different vibration analysis techniques, namely RMS, crest factor, kurtosis, and shock response spectrum. The dotted black lines on each graph shows when lubricant was added to the toggle. The 4 analysis techniques failed to show any change in the data distribution when lubricant was added. This goes to say that the clamping period does not provide valuable information relating to the lubricating condition of the toggle. For this reason, the research focus shifted from the clamping period to the unclamping period. RMS, crest factor, kurtosis, and SRS indicator were similarly used to analyze the unclamping period. The RMS plot did not show any significant change in the data distribution when lubricant was added to the toggle. However, it is apparent that the data distribution for the crest factor, kurtosis, and SRS indicator changed significantly when lubricant was added to the toggle. It can be observed in these three plots that at the start of the cycle, the data distribution is relatively low and stable. In both the kurtosis and SRS indicator, the data distribution remains low and stable for a period of time before eventually experiencing an exponential growth. A further analysis of the data collected using the SRS indicator highlighted a bathtub-like distribution. After lubricant is injected into the toggle, the SRS indicator decreases, as shown by the blue arrows. The SRS indicator later remains stable for a period of time, as represented by the green arrows. This stable period is the normal operational life of the lubricant. The stable operation is then followed by an increase in failure rate, as represented by the yellow arrows. A robust real-time condition monitoring system should hence be able to trigger lubrication when the system is at the increasing failure rate. A real-time condition monitoring system was designed using the knowledge gathered from this study. The upper plot shows a cycle-by-cycle display of the shock response indicator. The instantaneous slope of the SRS indicator is then calculated and plotted on the second plot. The final display uses the z-score outlier test to determine when the instantaneous gradient exceeds the distribution's 95% confidence interval. Relubrication should occur when the z-score becomes larger than the grub's critical value.